Let us discuss about individual systems. A system in which the concentration of hydronium ion, that is the H plus, is equal to the hydroxide ion, that is the OH minus, will have the pH equal to pOH. Such a solution is considered neutral. For pure water, the concentration of hydronium and hydroxide will always be equal. Hence, pure water is always neutral, irrespective of temperature. At 298 Kelvin, the neutral pH is 7, but remember, it would change with the temperature. A solution in which the concentration of hydronium ion, that is H plus, is greater than the hydroxide ion, that is OH minus, will have the pH less than pOH. Here we need to remember that it is the negative log. So if the concentration of H plus is greater than hydroxide, the pH is less than pOH. Such a solution is considered acidic. A solution in which the concentration of the hydroxide ion, that is OH minus, is greater than the hydronium ion, that is the H plus, will have the pH greater than pOH. Such a solution is considered basic. Now let's consider a question. Let's see. Kw. It means ionic product of water, hence it need not be told. So Kw at 363 Kelvin is 10 raised to power minus 12. Just remember, Kw increases with increase in temperature. The temperature here is 363 Kelvin, that is more than 298 Kelvin. So the question is, Kw at 363 Kelvin is 10 raised to power minus 12. Calculate the pH of pure water at 363 Kelvin. Is it acidic, basic, or neutral? So let's answer. The question says it is pure water. Hence, the concentration of H plus and OH minus are same. That means pH is equal to pOH. Now, pKw is equal to pH plus pOH. So, pKw is equal to twice of pH. Now, pKw is 12. So, 12 is equal to twice of pH and pH is equal to 6. Now, you might be tempted to say that pH is less than 7. Hence, it should be acidic. But here are two things that you must remember. pH 7 is neutral only at 298 Kelvin. Here, the temperature is greater than that, so the neutral pH will be different. Further, the question clearly states that it is pure water, and pure water is always neutral. Now let's consider some other solutions. Let us take a solution which contains 0.1 moles of HCl, hydrochloric acid, in 1 liter of solution. Now this becomes a 0.1 molar solution of a strong acid. Being a strong acid, HCl is completely dissociated. Hence, while writing the equation of dissociation of HCl, there is no need to put the equilibrium arrow. One-sided arrow is hence used. HCl dissociates to give H plus and Cl minus. 0.1 moles of HCl gives 0.1 moles of H plus and 0.1 moles of Cl minus. The concentration of hydronium ion H plus from HCl is equal to the concentration of HCl added. Now if you look at the autoionization of water, it is very clear that HCl increases the concentration of H+, which is the product of this equilibrium reaction. Increase in concentration of product will shift the reaction towards the reactant, that is backward. In this case, it would mean that water would ionize less. The dissociation of water will decrease. In this way, HCl actually suppresses the ionization of water. The suppression of ionization of a weak electrolyte by the addition of a strong electrolyte which has one ion in common to the ions produced by dissociation of the weak electrolyte by increasing the concentration of that ion is termed as common ion effect. Due to the suppression of ionization of water, water now does not release the amount of H plus as before. If we are considering the temperature as 298 Kelvin, it would mean it does not release 10 raised to power minus 7 moles of H plus as before. Let us say the amount released now is X. The total concentration of hydronium ions will be the sum of hydronium ions from hydrochloric acid and water. Now, the concentration of hydroxide is the same as the concentration of hydroxide obtained only from water. Since water is the only source of hydroxide in this solution, HCl does not release any hydroxide. It releases chloride. So, we get OH minus is equal to the OH minus from water itself, and that is X. HCl is a strong monobasic acid. Monobasic acid means it releases only one H plus in the solution. The word strong with HCl tells us that it completely dissociates, and monobasic tells us that each HCl unit releases one H plus. Hence, for HCl, the concentration of H plus from HCl is equal to the concentration of HCl itself. As the concentration of HCl is 0.1 molar, so the concentration of H plus from HCl also is 0.1 molar. As the concentration of HCl is 0.1 molar, so the concentration of H plus from HCl also is 0.1 molar. Remember, HCl is a monobasic acid. If we had a strong dibasic acid like sulfuric acid, H2SO4, the concentration of H plus from acid, considering the acid completely dissociates, will be double of the concentration of acid. The total concentration of H plus is equal to the concentration of H plus from HCl and water. At 298 Kelvin, Kw is equal to the product of the concentration of H plus and OH minus, and it becomes 10 raised to power minus 14. The concentration of H plus is 0.1 plus X. 0.1 from HCl, X from water, while the concentration of OH minus is simply X. So it becomes 10 raised to power minus 14 is equal to 0.1 plus X multiplied by X. Now here, we do not know what this value of X is, but we can think that this X is quite small. Now whether to see whether this X should be included with 0.1 or it should not be included with 0.1, what we simply do is just neglect it. If we simply neglect it, we get 0.1x is equal to 10 raised to power minus 14. Now this expression tells us that the value of x would be somewhat similar to 10 raised to power minus 13. Now, the value of x should be actually a little smaller than 10 raised to power minus 13. In such situation, it becomes quite appropriate to neglect the concentration of H plus coming from water, that is X. This is the quantity present in the addition terms, so it is easily neglected. This would mean that the total concentration of H plus is simply the concentration of H plus we are obtaining from hydrochloric acid. So it means H plus total is simply the H plus from HCl, which is equal to the concentration of hydrochloric acid. This, which is equal to 0.1. The pH is the negative log of hydronium ion. So it becomes the negative log of hydronium ion concentration from only HCl. This in turn is equal to the concentration of hydrochloric acid itself. So we simply get the pH to be 1. Now let's consider the case of 0.1 molar sodium hydroxide. The entire calculation is the same as hydrochloric acid, but here instead of H plus we would consider the concentration of hydroxide ion. Water again dissociates to give H plus and OH minus. Here again we consider the concentration of H plus coming from water to be X, OH minus from water to be X. Now sodium hydroxide, being a strong electrolyte, completely dissociates to give Na plus and OH minus. We have the concentration of NaOH as 0.1 molar. So when it dissociates, it gives 0.1 molar of sodium ions and 0.1 molar of hydroxide ions. The concentration of hydroxide ion total will be the concentration of hydroxide ion from sodium hydroxide plus the concentration of hydroxide from water. Now here it would become the concentration of hydroxide from NaOH plus X, that is from water, that is equal to 0.1 molar, that is the concentration of sodium hydroxide, plus X, the contribution from water. Kw is equal to the concentration of H plus into concentration of OH minus. If we take the temperature as 298 Kelvin, then it becomes 10 raised to the power minus 14 is equal to the concentration of H plus multiplied by the concentration of OH minus. In this case, it becomes X multiplied by 0.1 plus X. Again, neglecting the value of X, we get 0.1x is equal to 10 raised to the power minus 14. This calculation simply tells us that the value of X is actually slightly less than 10 raised to the power minus 13. It justifies that X must be neglected. So, the concentration of OH minus total will be equal to the concentration of OH minus that we get from only sodium hydroxide. Sodium hydroxide is a strong monoacidic base. So this becomes equal to the concentration of sodium hydroxide, that is 0.1 molar. Finally, getting the negative log of the concentration of hydroxide will give us POH. POH is equal to the negative log of OH minus. That is equal to the negative log of OH minus from sodium hydroxide, which is further equal to the negative log of sodium hydroxide concentration, which is equal to negative log of 0.1, and that's equal to 1. We know the sum of pH and POH at 298 Kelvin is 14. So the pH is 14 minus POH, that makes it 13. Let's answer a question. Calculate the pH of 0.01 molar HCl. Now, the answer. The concentration of H plus from HCl is 0.01 molar. The concentration of H plus from H2O would turn out to be 10 raised to power minus 12. Again, the concentration of H plus from water must be neglected. Hence, pH is the negative log of HCl concentration. That means it is the negative log of 0.01 and that's 2. pH is equal to negative log of HCl concentration equal to negative log of 0.01, that's equal to 2. Let's have another question. Find the pH of the final solution made by mixing 1 milliliter of 0.1 molar sodium hydroxide with 999 milliliter of water. The answer to this question would be molarity of sodium hydroxide given to us is 0.1 molar. The initial volume of sodium hydroxide given to us is simply 1 milliliter. The final volume of the solution is 1 plus 999 milliliter, that is 1000 milliliter. The final concentration of sodium hydroxide, we use the molarity equation, that is M1V1 is equal to M2V2. That becomes 0.1 multiplied by 1 is equal to M2 multiplied by 1000. So M2 is 0.1 multiplied by 1 divided by 1000. So it is 0.0001 molar or simply 10 raised to power minus 4 molar. Now the concentration of OH minus from sodium hydroxide is 0.0001 molar or 10 raised to power minus 4 molar. The concentration of OH minus from water using the same previous calculation is 10 raised to power minus 10 molar. Again, much smaller than the concentration of OH minus from sodium hydroxide. Hence, again, it need not be considered. pOH will be equal to negative log of sodium hydroxide concentration, that is equal to negative log of 10 raised to power minus 4, that is equal to 4. Now pH is pKw minus pOH. Considering the temperature at 298 Kelvin, the pH is 14 minus 4 and that comes out to be 10. Let's consider another question. Calculate the pH of completely dissociated 0.0005 molar, that is 5 into 10 raised to power minus 4 molar H2SO4 sulfuric acid. Now here we have the log 5 which you might need is equal to 0.699. H2SO4 is completely dissociated to give you 2H plus plus SO4 2 minus. Answer. Now here we must remember sulfuric acid is dibasic acid. The concentration of hydronium ion from sulfuric acid in completely dissociated sulfuric acid will be the double of acid concentration. We have sulfuric acid as 0.0005 molar. 1 mole of sulfuric acid gives 2 moles of H plus and 1 mole of sulfate. So 0.0005 molar sulfuric acid would give twice of it, that is 0.001 molar H plus and 0.0005 molar sulfate ion. The concentration of H plus from sulfuric acid will be twice the concentration of sulfuric acid. That is twice of 0.0005, which is simply 0.001 molar. The contribution from side of water is 10 raised to power minus 11, hence must not be considered. So, pH is simply the negative log of 0.001 and that's equal to 3. Just understand, the log 5 is given just to confuse. It is not required. Let's consider another question. Calculate the pH if 200 milligram of sodium hydroxide having molar mass 40 grams per mole and 185 milligrams of calcium hydroxide having molar mass 74 grams per mole are present in 1 liter of solution at 298 Kelvin. Let's have the answer. Here we have two bases in a single solution. Hence, we must find the contribution of hydroxide from each base individually. The negative log of the total hydroxide concentration will give us the pOH. Now, the total hydroxide concentration is the hydroxide concentration from sodium hydroxide and hydroxide concentration from calcium hydroxide. Sodium hydroxide is a monoacidic base. That means it gives only one OH minus per unit, while calcium hydroxide is a diacidic base. It releases 2 OH minus per unit. Hence, the contribution of OH minus from sodium hydroxide is equal to the concentration of sodium hydroxide, while the contribution of OH minus from calcium hydroxide will be twice its concentration. The moles of sodium hydroxide is the mass of sodium hydroxide divided by molar mass of sodium hydroxide. That is 200 into 10 raised to power minus 3 grams divided by 40 grams per mole. While the moles of calcium hydroxide is mass of calcium hydroxide divided by molar mass of calcium hydroxide. That is 185 multiplied by 10 raised to power minus 3 grams divided by 74 grams per mole. The concentration of hydroxide ion from sodium hydroxide is the same as the moles of sodium hydroxide. Here, again it will be 200 into 10 raised to power minus 3 grams divided by 40 grams per mole. But the contribution of hydroxide ion from calcium hydroxide is twice the number of its moles. That is 2 multiplied by 185 into 10 raised to power minus 3 gram divided by 74 gram per mole. The total concentration of OH minus would be 200 into 10 raised to power minus 3 grams divided by 40 gram per mole plus 2 into 185 into 10 raised to power minus 3 gram divided by 74 gram per mole, and whole is present in 1 liter, that is 1 decimeter cube. Calculating the value, the concentration of OH minus from both comes out to be 0.01 molar. Taking the negative log of this concentration, we get the pOH as 2. The temperature is 298 Kelvin. So Kw is 10 raised to power minus 14. pKw is 14. So pH is 14 minus 2. That is equal to 12.